Hello, my name is Bo René Winkveld and I will be presenting on dictionary learning and specifically image denoising using dictionary learning. Dictionary learning is the field of finding common elements called atoms to describe uh, an or a set of objects. So if we look, for example, at this example with the smiley faces, we can see that these smiley faces are composed of big circle, small circle for the eyes, and a line for the smile. And these are individually called atoms, and together they make a dictionary. And in the field of dictionary learning, our focus is mostly on the learning. How do we find a dictionary that is representative of the thing that we want to describe, represent? And a common method for that is the K singular value decomposition method. And since we want to do image denoising, the original author of this method published a paper on specifically this algorithm applied to image denoising by Allet. And there is one notable thing about their algorithm, because for images of the size n by m pixels, they use data structures and matrices of the size nm to the fourth, which grows really rapidly. So our main research question is, can we, for this method, reduce the memory cost? So that brings us to the methodology. And we will start by dividing the image into overlapping blocks of the size n times n, and then we will be trying to apply dictionary learning on the blocks rather than the big image itself. What we will do is we will assume these blocks independent, which will allow us to compute things locally and indeed reduce the memory size required. And that brings us to our data model. So we assume that the noisy image is equal to the noiseless image plus noise. And the noise is assumed to be a zero mean white Gaussian noise. And for the dictionary learning, it's actually applied not on Y, the noisy image, but on X. So the noiseless image, which over here we have the optimization criterion. And for this dictionary learning, we will apply the KSVD method, in which we will find the sparse vectors using the orthogonal matching pursuit method. And since we don't know X, we will have to estimate it, and we will do that using a maximum likelihood estimator combined with the Lagrangian to make X subject to the minimization constraint imposed by the dictionary learning. And that results, because of the independence, we can do it locally on each block individually. So over here we also have the optimization equation for block I of X, which is as follows. And then this leads to a closed form solution below, and this will be iteratively used alongside the KSVD method. And that brings us to the results. So we will start with the validation of the model, and we can see here in the middle is a noisy image with 5 gray levels of noise invariance. And we can see that if no iterations are taken and the dictionary learning is applied directly using the following dictionary, which is seen here in the upper left. Then the lower left shows the result, which we can see. It is a bit hard to see, but um, there is visually less noise, but it's also very smooth. Um, and then after 10 iterations of our algorithm, we can see the dictionary on the top right, which looks much different. And below we can see the resulting image reconstruction, which is heavily distorted. And well, by looking closely and comparing it to the other image, you can see some contours of the objects inside of the image. Um, it is heavily distorted. Let us move over to the time requirements. So for each iteration takes around 42 seconds, of which it's computing the orthogonal matching pursue for 26 seconds and the rest in 16 seconds. This means that it's very heavily, that the computation is very heavy on the OMP side, which is expected since it is using a lot of inverse operations. Actually, it's using multiple inverse operations for each block inside of the image, which results in this high computing time. Now to discuss these results, we will start with the distortion. So currently, the current implementation of the method does not work because it causes a lot of distortion. And this can be due to two facts. So we see directly that the dictionary is updated incorrectly. And it could be due to the dictionary update step, which is taken from the KSVD paper. And it could have been that we did not apply it well within our framework, which resulted to incorrect adjustments. It is also possible that the image estimation update step can be non-converging in the iterative manner that we have implemented it. But for both of these reasons, we will have to, in future works, analyze both of these steps individually per iteration to see which one is behaving not properly. For the time aspect, the current implementation takes a lot of time. Each iteration takes more than 40 seconds, and the original paper uses 10 iterations, and we also use 10 iterations for denoising, which means that it can take several minutes for a picture. A possible way to improve the time is by doing subset training, where only a subset of all of the blocks are used in the training of the dictionary, which would reduce OMP calls, which are the most time consuming, along with the other computations. But it might be hard to implement because our current method, especially the image update step, requires the sparse representation of all the blocks to edit it. And that leads us to the research question. So, can memory cost be reduced? And the answer to that is yes. For the images of n by m with n by n patches, small n by n, they can go from this big number, which is very variable from image to image, and much larger, to simply relying on the dimension of the blocks themselves and how it is done in the original paper, they used 8x8 blocks, which would thus significantly reduce and also fix the amount of size needed, which would be very good for low memory devices, for devices that don't have much memory available that do need to do this processing. Yet it also relies on the independence of different batches, which can reduce the effectivity in the denoising, since this is utilized in the original method, and therefore there exists some trade-off between noise reduction and memory. And in order to assess this better, this method needs to be compared in effectivity to the original method, and also a low memory method like directly applying KSVD onto the noisy image instead of on the noiseless image. Even though the current implementation causes a bit of distortion in the image, if this distortion can be evaded, it does give a big improvement in memory usage. And that brings us to the end of the presentation. Thank you for listening.